This is the graph of a standard normal variate that we have, and you can see the mean is mu is 0, and we have two variates at alpha by 2 and alpha by 2, and for the positive and the negative. So to understand this, let us say we have two statistics T1 and T2, and T1 is less than T2. Probability that the random interval T1, T2 includes the true value of population parameter theta. So if I have two variables T1 and T2, two statistics, sorry, T1 and T2, then what is the probability that the true value of population parameter theta is included in T1 and T2, interval T1 and T2? That means if I see this figure, the whole area is 1 from the ones which are marked with the blue bars, from this till this, the whole area is 1 minus alpha. So, and this tail is alpha by 2, this tail is alpha by 2. So the probability that the population parameter, this, let's say this is the sample, if this is my sample mean and here is my population mean, or something like that, right? Could be here, it could be here, or if this is my population mean, this is my sample mean. So what is the probability that the population parameter, now when we say population parameter, it could be any parameter of the population, not only just mean. So let us say theta. So what is the probability that the population mean belongs to this interval, or it is within this variate and this variate, translated into standard normal distribution form? So that is represented in the format T1 is less than equal to theta is less than equal to T2 is 1 minus alpha, because we are saying 1 minus alpha is the area, is this area is 1 minus alpha, and T1 is this point, T2 is this point, which we have marked as z alpha by 2, and this negative z alpha by 2 or z alpha by 2, whichever whatever you want to pronounce it. So this is represented in this format, 1 minus alpha. Okay, so then we say that the random interval, this random interval T1 T2, this random interval is known as 1 minus alpha % confidence interval for the unknown population parameter. So this is 1 minus alpha %, when we say percent, we say 100% confidence interval. Okay, this is a basic understanding of confidence interval. We can say CI as well for the unknown population parameter theta, and 1 minus alpha is known as confidence coefficient or confidence interval. So basically we say this one as the confidence interval, 1 minus alpha, right? Here important thing to note and very important thing to understand is the alpha does not depend on theta, right? So what is the significance of this kind of pictorial representation or this kind of distributions in a very common sense? In a very common sense, we can understand that if I have a standard normal distribution curve like this, then obviously, with a certain confidence interval, let us say T1 and T2, I'll be able to judge from the sample what is the population parameter, and based on a certain confidence interval, we will subsequently see how to formulate it. But from a general understanding perspective, if we are sure that our population parameter is a mean, population mean, and let us say we are trying to find out what is the population mean, our theta is a population mean, let us say, just for example, and we have found one estimator in the sample, maybe sample mean, right? So sample mean is trying to estimate population mean, and if this interval is, let us say this area is 0.95, then we can say the 95% confidence interval. So with 95% confidence interval, that the population mean will lie between this interval and this interval. In this T1 and T2, we are 95% sure. So in a real world, if you increase the number of samples, obviously either your increase the sample size, then obviously you will have a better or smaller confidence interval, so that you can be more sure about the population parameter. So that's a separate topic which we will see in future videos, but as of now our target is to estimate the confidence interval. So first we'll start with the normal distribution, how to estimate. So the confidence interval for population mean, confidence interval for population proportion, and confidence interval for population variance, these are the three things that we will see. So one is the confidence interval for population mean. So population mean. The second is CI for population proportion, and third is the CI for population variance. So how exactly we can estimate the confidence intervals, the CIs for these kind of population parameters? These are parameters called theta, right? Now to understand this, we'll first start with one simple example, the number of cases. The first case we will go for the population mean, as we said here. So confidence intervals for population mean. Now in population mean also we can have a case, let us say case A, where we know population variance. So case A, when population variance is known. Basically it means we know the population variance and we want to find the confidence interval for population mean. So our target thing to find out is the CI for population mean. And what do we have with us? Population variance. It is known to us. In that case, what we say is, and again, the population is a normal population distribution that we're talking about, and the sample is again the normal distribution samples that we're talking about, right? So in that case, the confidence intervals, one which we saw last time, is this is what is a Z alpha by 2 sigma by root n. So this is the sample mean plus minus Z at alpha by 2, that is the standard variate at alpha by 2. Sigma is the population, I said population variance is known, and this is the sample size. So what we normally do is we find the sample mean using the sample observations that we have. Then we find out the we have this value, and we find the corresponding standard variate from the standard table. So if I have a 95% confidence interval, then what we do is, that is 1 minus alpha is equal to 0.95, right? So the alpha will be 1 minus 0.95, and that is where is equal to 0.05 and alpha 2 will be 0.025, and this is where we find out. I mean, just an example. We're not going into solving the mathematics part, but this is how the confidence intervals are derived. Now if you want to see the derivation of this formula, so let me show you how to derive this interval. And I will not go through each and every derivations. I can just show you one derivation, how to find out. So the normal example, let us say x1, x2 and xn be a random sample of size n. So it's a random sample taken from a normal population it is taken from a normal population mu sigma square, right? When sigma square is known, we have said that population variance is known, so sigma square could be any value. We can even say sigma 0 square, right? It is a known value, for example sake. Anyway, so this implies our sample mean distribution will also follow a normal distribution with sigma square by n. We are aware of this. We have seen in the previous slide videos, and the variate z will be x bar minus mu by sigma by root n, and we know that if it is a population variance taken in the standard normal variate, then this follows a normal distribution. And we know, and as we know, what is that here? Probability density function of z. Again, we have seen this 1 by root 2 pi e to the power minus half z square, right? And z is from minus infinity to plus infinity. Now, distribution of z or z is independent of the parameter mu, right? So standard normal variate here, the distribution of z is independent of mu because it follows the standard normal distribution. Hence z or z can be used as a pivotal quantity or a pivotal quantity. So we can say from our previous knowledge that the standard variate at alpha by 2, if you remember the graph, is less than equal to z is less than equal to z at alpha by 2 is equal to 1 minus alpha, right? That is very obvious and very clear, because the probability or the area of the graph from this point to this point is 1 minus alpha, as we have seen in the previous slides. So this means P alpha by 2 is less than equal to, now we translate this to x bar minus mu sigma by root n, which is equal to the same thing, c alpha by 2. This is again equal to 1 minus alpha, right? I mean, it's not a very complicated thing, it's a very simple derivation actually. And what we can do, we subtract x bar from each term, right? So the previous term from the previous term, okay, let me write the previous term so that you don't forget again. So previous term was p minus z. This is what we derived, is less than equal to x bar minus mu sigma by root n is less than equal to z alpha by 2 equal to 1 minus alpha. Now subtract minus x from this will give you p minus x bar. What is x bar? It is a sample mean, right? Minus z at alpha by 2 and multiply is less than equal to minus mu less than equal to minus x bar plus z alpha by 2 sigma by root n. Well, what I have done is I have multiplied each of these terms with sigma by root n and subtracted minus x. Okay, so this is what I got, and if I convert this into the whole of negative, the inequality will change. So the inequality will now be the x bar plus z at alpha by 2 sigma root n is greater than equal to mu is greater than equal to x bar minus alpha by 2 sigma by root n, and then you transform into less than equal to inequality. I mean, it's a simple mathematics, it's not a big deal, you can do it yourself. I just thought of showing you how do we convert this, okay, into x bar plus z at alpha by 2 sigma by root n. Now this whole thing is equal to 1 minus alpha. The right side remains unchanged. So what it means is, the coming back to our estimation target or the outcome, we were trying to find out the confidence interval for population mean, and which is a normal population we are talking here. This is when variance is known, right? I just showed you how to calculate the confidence interval. I'm not going to show it for each and everything. So this will be what we found out is x bar minus plus or plus minus z at alpha by 2 sigma by root n, right? So this is the formula. Now case number B, as I said, variance can be unknown also, the population variance can be unknown. So for B, this is another case, Ci, when Ci for the confidence interval for population mean, when population variance is unknown, what is the meaning? So here we are using population variance to find out the control interval, confidence interval, but here we don't have the population variance with us in the next case. In that case, we will use our knowledge of t distribution, and that is the reason I first went through the t distribution, chi-square distribution, Fisher distribution once again before coming to this topic. So in that case, when we do not have a population variance with us, we have a sample variance. Obviously we can find the sample variance, and this is what we have seen many times, is equal to I is equal to 1 to n xi minus x bar whole square, and we know that the t distribution is equal to x bar minus mu by s by s sample deviation, standard deviation of the sample, by root n. This follows t distribution with n minus 1 degree of freedom. If you don't remember, please go to the previous video and see. There are 2 videos where I have discussed this in details. So degree of freedom is n minus 1, right? And we know why it cannot be a normal distribution here. So it follows a t distribution, and you can find out the critical value of t from the table. So the confidence interval in this case will not be in the with respect to z, it will be with respect to t. So it's x bar minus plus t with n minus 1 degree of freedom, n is the sample size, at alpha by 2, this whole into s by root n. This is the one. This is the confidence intervals for the population mean when population variance is unknown. I am not going to show you the derivations once again live. Here I have shown you the previous one. In this case I have shown you the derivations. This one you can try yourself and find out. So it's again the same concept. You can try to find out this one. Now there can be a large sample. See, if you go to the t table, you will not be finding data for a degree of freedom more than 30 or so. So when n is greater than 30, how do we find out? We have said that see, as long as it is within 30, we say that the confidence intervals for population mean is x bar minus plus the t distribution t variate with this one degree of freedom alpha by 2 s by root n. But if it is n is greater than 30, then it tends to behave like a normal distribution, and we can say that in this case, yes, it will follow a normal distribution because we do not have a t value in the table, and we can use it the same. Now this proof I'm not going to discuss here. So, and this will follow a normal distribution. So if it is a more than 30 degree of freedom, or sample size is more than 30, the confidence intervals will be minus plus x bar minus plus, same as a standard normal distribution, s by root n, right? So here we can continue to use the sample variance as one of the parameter, even considering the fact that it is a large sample size. Anyway, so we'll quickly go to the next cases where the confidence interval for population proportion, and the last case the confidence interval for population variance. I will cover these remaining two in the next video to keep this video reasonably short. Thank you.